Welcome to the lecture on leader election. So in this lecture what we will study is that we will be given n nodes and in a distributed fashion these nodes need to run an algorithm where they need to elect a leader. So we are not assuming any faulty processes here. So we are assuming that they will elect a leader just by exchanging messages. So we will start with a ring overlay where all the nodes are arranged as a ring. So every node can either send a message to its clockwise successor or its anti-clockwise successor, or send a message to the left or to the right. That's the only messages that it can send. So this network is kind of simple and constrained. So we will look at an order n square message complexity algorithm and then refine that to an order n log n version. And then we will consider another version of the problem where the processes are arranged as a tree. So when they are arranged as a tree, we will find that they have better properties. So we can reduce this n log n further and make it in the ballpark of order n. So let us discuss leader election algorithms. Okay. So I stand corrected, not the ballpark of order n, but order n. So let's go to the tree part and we will discuss. But first we solve the simpler problem with rings. So in a ring based overlay, the idea is that we need to choose that process that has the smallest ID as the leader. It has the smallest ID. So of course there is an asymmetry. In a sense, we are saying that look, a node with a large ID or not the smallest ID cannot be the leader, but that's fine. In any distributed algorithm, there is some asymmetry. If you do not have asymmetry, there is a classic theorem which says that you actually cannot make progress. So I'll explain with a simple example. So let us consider a corridor. So let's consider this person to be Alice, this person to be Bob. So you would have often seen that if without any understanding beforehand, if let's say two people are coming face to face in a narrow corridor, Alice is moving this way, Bob is moving this way, then they can collide. Then what Alice will do is Alice will move to her left. What Bob is going to do is he's going to move to his right, and then they will again collide. Okay, they will again be face to face. Again Alice will move, but Bob will also move, so they will again be face to face, they will again collide. So this does happen many a time with us, particularly when we want to, when we come face to face with somebody in a narrow corridor. So this does happen. So then typically what happens is one person says that, okay, look, I am stopping, you go. But what if the other person also says that? In this case, it is provable that unless we somehow break the symmetry, right? So unless we say that, okay, between you and me, whoever has more letters in his name, that person gets to move, the other person gets to stand. And if we have the same number of letters in our names, then let's say let us break the tie by the first letter, otherwise by the second letter, and so on. So in that case, there is a tie breaking, there is an asymmetry we are introducing to essentially solve this kind of a situation. So this, for Hindi speakers, there is a name for this, it's called Pehle Aap. And for non-Hindi speakers, what this means, this is like a courtesy which is given to the other person saying that you may cross me first. But if the other person also returns the courtesy and he says, no, not me, but you cross me, again there will be a face-to-face situation. Given the fact that we have that, breaking the symmetry and introducing some level of asymmetry is very important. So given the fact that we are only constrained in terms of the messages we will send either to a clockwise neighbor or to an anti-clockwise neighbor, breaking the asymmetry is even more important because we can't send messages to others, and clearly we do not want to break the rules by having a centralized algorithm. So it should not be the case that we send messages to one node, but again which node, right? So that node has to be the leader, but no leader has been elected. So we still want to have a distributed algorithm and kind of, let's say, compute the minimum ID, and then we all agree that that node is our leader. So we'll discuss the Chang-Roberts algorithm. So every node P, so the convention we will assume over here is that I am node P and the other node is Q. So always I am P and the other node is Q. So if, let's say, if one node P is the initiator, which means that, I'm just starting the process of leader election, but you need not have one initiator, you can have many initiators. So then it will look at its state variable and set it. So it will set the state variable to find, which means that node P is in the process of finding a leader, right? Electing a leader. So what it does is that it sends its own ID to its neighbor. Doesn't matter, clockwise neighbor or anti-clockwise neighbor, doesn't matter. You choose a direction, it sends its own ID to its neighbor. As long as the state is not equal to leader, which means that the state indicates that the leader has been elected, we continue the algorithm. So what do? We come to line 3, So we receive a message from Q. Alright, so we have an overlay like this. And so I am node P. I send my ID to my neighbor, so on and so forth. And finally, from my neighbor, I receive a message. So I stand slightly corrected. I don't receive a message from Q, but what I actually get is I receive a message whose content is Q. Okay. So I receive a message from my neighbor from the other side, where the content of the message is Q. But if that is the same as the ID that I had sent, then I declare the state to be leader and I say that the operation has finished. So what I'm basically saying is that, let me maybe draw this, or let's go to another one of our bigger diagrams. So what I'm saying over here is I am node P. I send my ID to my neighbor. It does something, we don't know what it does. Whenever I get so I can also get messages from my neighbor, because my neighbor can also send me messages. So let's say my neighbor sends me a message with contents Q, right? My neighbor is not Q. The content is Q, right? Even though, broadly speaking, we do assume that P and Q in the general case are different. But let's say I get a message from my neighbor whose contents is Q. If P is equal to Q, so we are of course making the assumption here, one assumption that is being made, that every node has a unique ID. Without this, our system is not possible. So you can assume it's the IP address which is, for example, unique, or there is some other way of providing a unique ID. So we are not getting into that. But once we have said that every node has a unique ID, and let's say this direction is clockwise. So from my anti-clockwise neighbor, if I get my own ID back, then I say that, look, the algorithm is terminated. I set the state equal to leader, which basically means that as far as I am concerned, a leader has been elected and the leader is me. Otherwise, if let's say I get Q from my neighbor where Q is less than P, which clearly means that I am not the leader. Alright, so in this case, I am the leader. In this case, I am getting a message from my neighbor with a value which is lower than my ID, and I am P. So if my state is find, I set my state to lost, which means that I am not the leader. Fair enough, that is an expression in humility. That is the reason being that already another node exists whose ID is lower than P. So that node could be the leader, or some other node whose ID is less than the ID of that other node. That's fine, but the leader is not me. So if this is the case, I just say I have lost and that's it. Then what I do is I propagate the value Q to next P. In the sense, next P is my neighbor, is my clockwise neighbor. So I just propagate the value Q to next P. Alright, fine. So then this else is basically if P is equal to Q or if Q is less than P. This else is basically the else for if P is the initiator. So of course here there should be one end over here which I'm not showing on the slide and another end for the while loop. So let's assume that these ends exist. So if P is initiator, then you do it, but else means that P is not the initiator. And so if P is not the initiator, it basically means that P is not interested. Okay, P is not interested in becoming the leader, then of course there is no problem. So then what it does is that it receives Q from its anticlockwise neighbor and it simply forwards the value of Q that it gets to next P. And then if it is sleeping, it just sets the state to lost, saying that look, I don't care, but anyway, in any case, I am not the leader. And I am also not interested in becoming the leader. So essentially, I have no stakes in the game. So as far as I am concerned, my job is to only forward, and I am doing the job of forwarding. So let us now come back and summarize. I'll get rid of the ink on the slide. So the idea basically is that if P is initiator basically means that I am interested in becoming a leader. Then of course if I am interested, then what I do is I propagate my own ID down the overlay. And let's say my own ID comes back to me, which means that nobody absorbs it. This means that every single node, this condition should have held true, which means that my ID is actually the minimum. That's the reason my ID came back to me and I became the leader. Otherwise, at any point, if my ID was not the minimum, it would have been absorbed and the message would have been dropped. In the meanwhile, what I do is, if I receive a message from my neighbor, and if let's say that message has a lower ID than mine, then clearly I am not the leader, so I set my state to lost and I just propagate the message down the ring. And of course, this condition is not handled. The reason is that I don't do anything. If let's say I get a message with an ID which is greater than mine, so clearly the originator of that message is not the leader. So I don't do anything. I just drop the message and I don't propagate it. So ultimately, if my message ends up being propagated down the ring via all the nodes and it comes back to me, which means this condition holds, then this means that I am the leader because nobody absorbed the message. Given the fact that nobody absorbed it, it basically means that my ID must be the minimum. And of course, if I am not interested, I just propagate the message down the ring. So what is the message complexity? Well, worst case, you can have order n initiators. The leader's message is going to be sent n times throughout the ring. For other initiators, the message will be sent a maximum of n minus I times. So what is I? So let's say I am the second, I'm not the minimum, but I am the second minimum, but I am just beside the minimum node. So then if let's say this is the min and I am over here, then my message is going to propagate all the way till this point. And so it will propagate essentially n minus 1 times. Right? And let's say after the second minimum, the third minimum is over here, then its message will be propagated n minus 2 times. Okay? So if let's say this is kind of the worst case. So if I just sum this up, this comes to order n squared, which is a very standard result in algorithms. And it basically says that look, the worst case arrangement is when they are kind of arranged in ascending order. And so then the minimums message of course will go through all n hops. But the other ones will go n minus 1, n minus 2 and so on. And the arrangement of course here is that they are arranged in ascending order, right, around the ring. Alright. So given the fact that this is order n square messages, we should make some effort to actually reduce this. So one optimization is that globally kind of broadcasting to everybody is not necessary. We can do something better. So let's see what we can do. So here is an order n log n time, sorry, not n log n time, n log n number of messages algorithm. So see, the main reason for an order n square complexity is because we want each message to travel as far as possible in the ring, which is essentially in the ballpark of order n. And since we have a sufficient number of nodes that are traveling roughly the entire ring, we have an order n square message complexity. So instead of sending a message to everybody, can we find a way to filter the set of messages? A similar idea to Merkava's algorithm in mutual exclusion. So recall that the previous lecture was on mutual exclusion and we had discussed the Merkava's algorithm. So can we do something similar? So what we do is that we gradually kind of consider larger sizes of windows or gradually consider larger search spaces in a sequence of rounds. So we'll define what a round is. So what we do is that if we consider a ring, we define a window like this. Only one of its members can participate in the next round, and also these windows will gradually increase. So we'll see how. But essentially, the idea is that we create these small communities of nodes, and every community elects its own leader, and then these leaders participate, and again they form a community. So recursively, our idea is to somehow reduce the number of messages by creating communities, then a leader of a community, elect the leader of leaders, and so on. So if we can kind of factor in every round, if we can reduce the number of nodes that are participating in an algorithm by a factor of 2, that would be really great, because in that case we'll have a maximum of log n rounds. So the complexity, even if it is order n, will be bounded by order n log n, which is what we want. Right? So let's see if we can do that. The idea is you elect a leader, create communities, elect a leader out of community leaders, so on and so forth. So let's look at this algorithm. So what we do is that in this case, we send one message to the left and to the right. So the previous algorithm was unidirectional. This is bidirectional. So the message has 4 fields: probe, ID, 0 and 1. So we'll see in a second what they are. So what they basically mean, okay? So what they basically mean is, probe means it's a probe message, right? So probe is the message type. ID is my ID, okay? And ID is the ID of my node. So this is what, and 0 and 1 kind of establish how far the message will go. So let me explain with an example. So this will gradually be cleared, but at least out of these 4 fields, at the moment you just appreciate 2 fields, which are probe and ID. Probe is the type of the message, which means I'm probing for a leader, and ID is my current ID. So I send messages to my left and right. Others also do the same. Okay. So then let's say that I am a node. So let me maybe delete the ink. So let's say I am a node and I receive a message from my left or right neighbor. And let's say the message that I receive is equal to my ID. So akin to the previous algorithm, I declare myself as the leader, the temporary leader at least, leader as J, and I terminate. Okay. And so we will see why, but sorry, I stand corrected. It's not the temporary leader, it's the final leader. But what I'm saying is that, let's say in this process of receiving a message, if I receive a message which is my ID, so let's say that the message has passed through the rest of the nodes. So I'll declare myself the leader and I will terminate. But let's just keep going forward. Otherwise, if the message that I get, right, so in this case the message I get is probe jkd, if j is less than id, and furthermore d is less than 2 raised to the power k. So we are now in a position to define these 2 fields. So this field over here is the round number. Okay, fine. And this field over here is basically the distance from the originator. So if I say d is less than 2 raised to power k, so if this happens, which means that if j is less than id, and so which means I'm sending it like this, and let's say that my current id is j, my current id is id, and I get j, and j happens to be lower than my id, then it means that, let's say if I got the probe from the left, I send it to the right, which means I just propagate in the same direction, or if I got it from the right, I send it to the left. So what is the key idea? The key idea is, look, I got a message. The message has j as its identifier, and my id is called id, I and d. If j is less than id, it means that potentially I am not the leader, the other message's originator is the leader. So what I need to do is, I need to help it propagate further. So I simply propagate it in the same direction. In the sense, if it came from my right, let's say, I propagate it to my left, and it came from my left, I propagate it to my right. So I just make it go in whichever direction it was going, but with a small catch. So it's still a probe message. The identifier of the message is still j. Okay. This still remains as k. So k is basically the round number, which is the same. We don't increment the round yet. But we say that its distance from the original node has increased by 1. So this becomes d plus 1. Right. So what we do is we make this distance check. So this distance, so k basically gives you an idea of the size of the window. So what we are saying is that if, let's say, this is the original point, then we will have 2 raised to the power k points on this side and 2 raised to the power k points on that side. Okay, roughly. And furthermore, the maximum distance that you are allowed to propagate in either direction is 2 raised to the power k. The moment d becomes less than or equal to, then we bounce back. We don't propagate it further, we just bounce back. Alright? And every hop that we propagate, we increment this distance and make it d plus 1. So it is important that you understand what exactly is happening. So I'll write this once again. There are 4 parts to the message. Probe is the type of the message. ID is the originator. Then of course, let's say, well, if I were to, so then of course we have 2 more k and d. So k is the round number. So what I do is I consider arcs. So if, let's say, I consider an arc of nodes, right? So then, and let's say the originator is over here. So I pretty much consider 2 raised to the power k nodes clockwise and 2 raised to the power k nodes counterclockwise. So for me, this is the size of the window that I am considering. And as I move my message, my hop count increases. So the last field over here is the hop count. And what I see is, if I receive a message, I propagate it in the same direction. If it's going counterclockwise, I send it counterclockwise. If it is going clockwise, I send it clockwise until I reach the end of this window. Okay, so I send, so let's say, drawing it once again, if ID is over here and the ends of the window are over here, I send one message all the way up till here, one message all the way up till here, until I reach the end. And how do I know I reach the end? Well, every hop that I propagate, I increment the hop count until the hop count reaches the maximum, which is this. Alright. Now if, let's say, it reaches the hop count, in the sense I reach the end of the window, and at the end of the window, same j is less than id holds and d is equal to 2 to the power k. So what did I say? We'll consider 2 to the power k nodes on this side and 2 to the power k nodes on the other side. So let's say at the end of the window, I still find j is less than id. In a sense, in this case, id of course is a local property for that node. But as far as we are concerned, the originator, at least from this path, has the minimum. We send a reply back. See, the message came from my left. I send a reply back to my left. In the sense, the reply path is the reverse path. So I just send a reply down the reverse path. So the field is again reply. You are sending a reply to the originator, which is j in this case, and k of course is a round number. So you send a reply back, and similarly the other side also sends a reply back. Of course, if this was the minimum on these sides. So one thing that is clear is that in this arc, if it gets a reply from both sides, so it clearly means that if let's say the ID of this node is j, j is the minimum in this window. We don't know about the rest of the world, which is like this, but that doesn't matter. At least in this window, j is the minimum. That's what we know. Okay. So gradually what we will do is we'll increase the size of the window, which is something we have promised. But till this point, things should be clear that we just define these small arcs in the circle, equal sized arcs on both sides. Simply send a message. And of course, a node can absorb it if the original ID is more than the ID of the node. But let's say it is less than the ID of the node. So I'm just repeating that we again have unique node IDs. So if it is less than the ID of the node just propagates it until it reaches the end of the window. From there, the message bounces back. So you send a probe message and what comes back is a reply. And let's say if you receive replies from both sides, this means that if the ID is j over here, it's the minimum in this window. Alright. So once we receive a reply, then what happens? So let's say I receive reply j, k from the left or from the right. So if j is not equal to my ID, then what I do is I just propagate the message. So if this is how the reply was going, this is me, I just send it until it reaches the ID. And similarly, you will have another reply coming from the other side if this ID is genuinely the minimum in this window. So let us say that so this condition doesn't hold, which means j is equal to ID. This condition comes. If you have received a similar reply from the other side, so this was from the left, if you have also received a reply from the right, then you clearly know that this ID is the minimum in this entire window. So now what you do is you increase the window size. So for this window, right, you are able to do it. So now what you do is you increase the window size. So again you send a probe message. So let's say this is the message type. ID is again your ID. But here is the fun part. The fun part is you increment the round number. You increment the round number and again you reset the value of the count and then you send a message. See, if you go back, this is exactly what we were doing. And again you come here, this is exactly what we were doing. Alright. Fine. So as you can see over here that, we were looking at this, we were looking at the distance and all of that. And similarly, what we now did is that instead of a k size window, we change it to a k plus 1 size window, which actually doubled it on both sides. So ultimately what will happen is our window will encompass the entire circle. And once the window encompasses an entire circle, this condition will hold true that my own message will come back to me. When that happens, I will know that I am the leader and I'll terminate. The termination criteria is similar to the previous Robert Chang's algorithm, which had order n squared messages. Alright, so let's look at the analysis. Let's compute the message complexity. That's not that easy to do, but we can still do it. Right, so again coming back, what we actually ended up doing is that we just considered larger and larger windows, one small window, then a larger window. Right, then we kind of double this, we start with this and then we start with this. And finally the window becomes the entire circle. And when that is the case, the termination criteria approaches. So what we can now see is the maximum number of winners after k phases is. So sorry, this is TW. Two winners can at the least be 2 raised to power k entries apart. Because within a window of 2 raised to power k, you cannot have two winners, right? One will absorb the messages of the other. So they have to at least be these many entries apart. Thus the total number of winners after k phases is n by 2 raised to power k plus 1, right? So if this is the minimum distance by which they are separated, then the total number of winners would be this and this interval plus 1. The total number of messages for each initiator in phase k is 4 times 2 raised to power k, which is simple. 2 raised to power k messages this side, probe messages 2 raised to power k messages on the other side, and similarly we'll again have replies 2 raised to power k this side, 2 raised to power k that side. So the total number of messages in the kth phase, alright, is this much times the number of winners in the k minus 1th phase, which is this much, which straightforward comes from here. So of course, these are the winners of the kth phase, but in this case, we will have to consider the winners of the k minus 1th phase because they are the ones who are going to participate in the kth phase. Phase and round is the same thing. Okay. So the total number of messages in this case, if I were to sum up from 1 to log n to the base 2, would be equal to this. Okay. So k, the maximum, it can go to log n because after that 2 raised to power log n will become equal to n. So one of the messages will come back to its place of origin. So this is the maximum value of k. So if I sum this up, this is not hard at all. And so pretty much what this will work out to be is that this part will pretty much work out to be a constant. And what you'll be left with is this n. And this is easily shown to be order of n log n. So hence we have order of n log n messages. That is the message complexity of this algorithm, where the difference between order n square and order n log n for a large number of nodes is pretty substantial. And this is clearly one of the ways in which we can elect a leader by gradually increasing the size of the window by a factor of 2. And other thing we did is we actively suppress messages in the sense that let's say in every window there is only one winner, and that winner is the one who's going to participate in the larger window, right? When we double the size of the window, this winner is going to participate. The rest of the nodes in the erstwhile window will not be initiators. So given the fact that we are suppressing messages, so this is same as saying that unless you win the quarterfinal, you can't participate in the semi-final. Unless you don't win the semi-final, you can't participate in the final. So we are suppressing messages. We are telling a lot of nodes not to send just because they lost a round. So after suppressing messages, what will happen is that ultimately very few winners will be left, and finally only one winner will be left. So now let us consider arbitrary networks. Okay. So creating a ring based overlay is in general difficult. Okay. The reason is that, if there's a large network with a large topology, how do we lay a ring through them? So this actually amounts to constructing what is called an Hamiltonian cycle, which is NP hard. So this is quite difficult to create. Instead of that, if let's say we have an arbitrary number of nodes placed everywhere, instead of passing a ring through them, having a spanning tree or maybe a minimum spanning tree is actually the best idea. We still don't know how to create a minimum spanning tree, but this is what we will study in the next lecture. But let's say if we could create a minimum spanning tree, which we all know it's easy to do, that would be really helpful. So here again we'll say the current node is P and the neighbor is termed Q. And let's say within the spanning tree that we somehow create, how we will create, we'll take a look at it in the next lecture. all the leaves, let's say degree equal to 1, these are the leaves, let these be the initiators, and clearly once a spanning tree has been created, every node knows whether it's a leaf or not, so it also knows whether it's an initiator or not. So given the fact that every leaf is an initiator, this is what we do. So if node P is an initiator, we set its internal awake variable to true, which means that the node P is now awake. So what it does is, let's say if this is a leaf and the leaf is an initiator, for each of its neighbors, so it will have a single neighbor though if it's a leaf, it will send a wake up message to Q. So as I said, I am always P and the other node is always Q. So if I am P over here, the other node is Q. So I will send a wake up message to Q. Alright. So what does this node do, which is a parent? So as long as while the number of wake ups is less than its number of neighbors, what does it do? It receives a wake up and it increments num wake ups. So which means that if I have a node over here which is getting wake up messages from the initiators, as long as it hasn't gotten a wake up message from one of its children, it will continue to receive, it will continue to increment the num wake ups variable. Furthermore, if awake is equal to false, so then it will set awake equal to true, it will wake up. And then what this node will do is that for each Q element of neighbor P, for each of its neighbors, it will again send a wake up message, right? So it will again tell its neighbors that, look, I am waking you up, alright? So fine, so all of its neighbors, of course the rest are initiators, but it could have another neighbor here, let's say its parent, it will send a wake up message there also saying that, look, now I am waking you up. Alright. So what do we do? Well, if you are an initiator, you wake yourself up, wake up your neighbors. If you are an internal node, and so then as long as the number of wake ups you have received is less than the number of your neighbors, you keep receiving them and you keep on waking up your neighbors. Fine, fair enough. Then what we do is, after the wake up state, what you do is that, so this is when you actually run the algorithm. So the algorithm is quite simple. So we have two variables over here, received and min P. So initially min P is my ID, which is P, and the received is 0. So for each internal node, as long as received is less than the number of children, right? So everybody knows how many children it has. It will continue to receive a message from Q. So where Q is the other node, so Q is the sender and I am P. So I'll continue to receive a message. And I will set this variable of mine, which is the received array. I am always node P, the other node is always node Q. So for its qth entry, I'll set it to true. Alright. And I'll increment the number of messages I have received. And then furthermore, what I will do is that the minimum that I maintain will be the minimum of the previous minimum and the value that I got from my child. So essentially what I do is, after I have woken up, every child sends its ID to its parent. The parent computes the minimum of all that it has gotten from its children and its own ID, minimum of the entire set. And once it computes the minimum of its entire set, right? So these are all the children and this is the parent over here. Once it does that, it sends the overall minimum, which means the minimum of all of its children and itself. It sends the overall minimum to its parent. So in this way, we kind of aggregate, we kind of walk up the tree, that all the children send their values to the parent computes the minimum, the parent sends the computed minimum to its parent, so on and so forth. It keeps on propagating towards the root. So which is quite simple. This is what you would anyway expect would be happening in a tree, a rooted tree particularly, where all the traffic would ultimately flow towards the root. Alright, so now what happens is, each child sends the value that it has gotten from its children to its parent. The parent computes the minimum for the entire subtree, then forwards it to its parent, which again does the same, which forwards it to its parent, which again does the same. Finally, the message goes to the root. Once the message goes to the root, we assume that the root has a special property, that the root is its own parent. Alright? And the root is its own child also. So the root is as such self-referential. In the sense the root is its own parent and own child. So then, what really happens is, so why do we make this assumption? Well, this will be clear when we look at other algorithms that also work with trees, but let us assume for the time being that this is the way that our tree has been created, that every node points to its parent and the root points to itself. That tells the root that it is the root. So what did we do in the last slide? What we actually did is we sent the computed minimum to the parent. So what would the root do? So if I would look at the root would essentially compute the minimum of the entire tree, which is the ID of the leader, wherever it is, and it will forward that to itself. So as far as the root is concerned, the root will begin execution at line 1, where it will receive R from the parent, right? So it will receive R from its parent, right? So the moment it is receiving a value from its parent, as far as the root is concerned, the process of leader election is over, alright? And now time has come to broadcast it. So what it will do is it will just compute the minimum of its own subtree, which in this case is the entire tree and the value it is getting. But again, this line is redundant, but nonetheless, the important point is that that res contains the ID of the system-wide minimum, and this will be broadcast down the tree to every single node. So out of this, it is possible that one of these nodes will actually be the leader. It will have the least ID. So every node will compare res with P, and if res matches P, then it means that that node is indeed the leader, so it will set its state equal to leader. Otherwise, it will set its state to lost. Fair enough? And then what every node will do is, so let's say every node P will send the message that it got from its parent regarding the global minimum to each of its children, right? And it will of course not send it to its parent, right? Q not equal to parent, Q is element of neighbor, which makes Q a child of P. So it will send it to each of its children, and they will again propagate the message downwards. So via this method, the leader can elect itself as the leader, and furthermore the message can be broadcast all over the tree, because every parent will forward it to its children, the child will again forward it to its children, so on and so forth. So what is the message complexity? Well, on every edge, we can send at most 2 wake up messages. We can send a proposal going up to the parent and the reply, which basically means with n in an n node tree, we will have n-1 edges. So the maximum number of messages is 4 times this, because as I said, 2 wake up messages in both directions and a leader proposal and a reply. So it's 4n minus 4, which is order n. So what we have seen in this lecture, actually let me go to the others, this is the last slide. So this of course are the references, we'll come to them in a second. But what we have discussed is that from order n square, which was a naive algorithm, we went to order n log n. So of course we did use a little bit of a trick here, this idea of this expanding window. But these two approaches were for rings. From here, we went to order n. But what we did is that instead of creating a ring, which also we argued is hard to create, we created a tree. And the tree we found is a very good overlay, in the sense that we are able to reduce our, it's very easy to send a message, it's very easy to compute the minimum, it's very easy to compute a bunch of statistics. And in that sense, a tree is a quite superior data structure as far as a distributed system is concerned, Of course, at this moment, we don't know how to take a set of nodes and construct a tree. Specifically a minimum spanning tree, because that would kind of minimize the total length, total sum of all the edges, right? You can think of it as the message sending cost. So if we somehow have a way of computing an MST, then we can very easily solve problems such as leader election. As you can see, the complexity will go down, and these problems can be solved very easily, subject to the fact that we know how to create one. So that is the subject of the next lecture. So these are the few references. So these are some very popular books on distributed algorithms. So they do have a lot of such distributed algorithms. So everything that we are doing at the moment are all asynchronous algorithms, in the sense there is no time base. When we discuss other kinds of algorithms, you might find synchronous algorithms, where let's say the algorithm will proceed in rounds, where it is assumed that let's say every node has sent exactly k messages each round, and then everybody knows when a round begins and when a round ends. So which means they have some sort of a shared time base. So we'll discuss such synchronous algorithms later. At the moment, we want to create an MST, a minimum spanning tree, given a set of nodes. So that is our next problem, because we have clearly seen how such a tree will be useful.